Okay.
Ecology. So ecology, I believe, is the first unit you'll have in AP biology. If you've taken apes before in the past, you have a really good understanding of what ecology is, and you'll probably do easy on this test. But it's also a very important concept and unit because it kind of shapes the way of everything that biology will be talking about.
And yeah, so like what we said, it's probably one of the easier units, but there are some graphs and math in it, but it's not too bad.
Yeah. So the first subsection of ecology is biological processes influence population density, dispersion, and demographics. Basically, population density is the number of individuals per unit area or volume, and that reflects the interplay of births, deaths, immigration, and emigration. Environmental, environmental and social factors influence the dispersion of individuals. Populations increase from birth and immigration, and decreases from death and emigration. Life tables, survivorship curves, and reproductive tables summarize the specific trends in demography,
Demography.
Yeah. So basically, that's kind of like the intro subsection. It's basically saying that births and immigration into a population make the total population number rise, while as deaths and emigration make the total population decrease.
Alright, so next, 53.2, the exponential model describes population growth in an idealized, unlimited environment. So obviously, some of you guys know what exponential is, so you got the population growth is just gonna go like that. When you have an idealized situation, nothing limiting, the more individuals you have, the more it's gonna increase. So if immigration and emigration are ignored, a population's rate equals the birth rate minus the death rate. So here's my note. This is the simplest equation, that change in population, which is n, over change in time, equals births minus deaths.
Yeah, and basically this little triangle is delta, and delta means any sort of change. You'll see that in biology or chemistry.
And of course, the math can, you go a little more in depth than that, and that's adding in things like immigration, emigration, defining birth rates and death rates. But then, yeah, you can ultimately use these numbers to make an exponential growth graph.
The logistical model describes how a population grows more slowly as it nears carrying capacity. So basically, when it's growing, right, you have your graph right here. When it's nearing the carrying capacity, that would be your carrying capacity. It'll start as an exponential, but then it'll turn out into sort of an S curve, come above the carrying capacity, then even out at the carrying capacity as it keeps going. Exponential growth cannot be sustained and for as long in any population, meaning that there's never going to be an unlimited amount of resources that are going to be available for the whole population. So that's why, as you see, as it grows exponentially, it slows down towards the carrying capacity, then furthermore stabilizes. That stabilization is what is the amount of resources equals the amount of the population that it can feed. A more realistic population model limits growth by incorporating carrying capacity, the maximum population size that the environment can support. So the carrying capacity, as you'll always see, is denoted as a K, as carrying capacity. And the environmental factors that play a part into the carrying capacity will make it stabilize at the carrying capacity point.
So the carrying capacity is basically anything that will limit a population's growth.
Yeah.
Right. So I think we're done with this, right?
Yeah. That's already there.
Okay. So life history traits are products of natural selection. So life history traits are evolutionary outcomes reflected in the development, physiology, and behavior of organisms. So we've got two reproductive models here in this section, and it's simulparity, which is that's a single large reproductive event. So an example will be this plant called the agave. It lives in the desert in a period of a good period, like with plenty of rain. That's when it reproduces, and then it dies immediately afterwards. Or it'd be like a spider who has a bunch of babies, and then they eat her afterwards.
Yeah.
So you have one reproduction event. And then heteroparity is multiple reproduction events. So that's like anything that can reproduce multiple times. Like here's an example of a sea turtle. They'll lay multiple clutches of eggs throughout their lifetime. I think that, yeah, and then we've got, of course, K selection and R selection. And high densities are for K selected, and R selected are for lower densities. So,
explain what K selection.
So K selection will maximize the population. That's lots of offspring, right?
Yeah.
And then R selected is fewer offspring but better survival. So many offspring will usually mean less survival of the offspring, and R selected will mean you only have a few but they have better chances of survival. So that's like an elephant who will raise their offspring very intently for many years, and then they're way more likely to survive.
Yeah. And then the next subunit is many factors that regulate population growth are density dependent. So it's dependent on the density of the population. So in density dependent population regulation, death rates rise and birth rates fall with increasing density. So basically that means the more population, the higher the population is, the death rates will rise and birth rates will fall. In density independent population regulation, birth and death rates do not vary with density, so that is with the multiple offspring, as Doyle was talking about, it's going to not affect it at all. They're going to have multiple offspring, it's going to be a huge population, and they're able to sustain that, so it's not dependent on the density. Density dependent changes in birth and death rate curb population increase through negative feedback loop, and can eventually stabilize a population near its carrying capacity. Density-dependent limiting factors include intraspecific competition for limited food or space, increased predation, disease, intrinsic physiological factors, and a buildup of toxic substances. So basically, it's saying that density-dependent are very their population is dependent on the amount of people in that population, as well as any outside forces such as disease, how much food is available, how much shelter is available, how much water is available. They're very dependent on how big the population is, as well as how much the land that they're at can hold their population.
Alright, and the last section is about the human population. The human population is no longer growing exponentially, but is still increasing rapidly. So, since about 1650, the global human population has grown exponentially. But within the last 50 years, the rate of growth has fallen by half. Differences in age structure shows that while some nations' populations are growing rapidly, those others are stable or declining in size. Infant mortality rates and life expectancy can vary widely depending on geographical location. So, both this chapter just explains the Earth's human population and what factors are affecting it right now. See, in developing countries like Afghanistan, the birth rate is much higher than in a slow growth population like the United States, or a no growth population like Italy. And this has to do with a variety of factors like healthcare, living standards of living, and other resources such as that. And ultimately, the human population will be limited, but it's not something that can easily be determined.
Yeah, and then back here you see, as the first starting of humanity, you had a rapid growth, so it would have a large base, so that's a large number of births, but also the life expectancy isn't very long because that is it's past, so it's basically pushing out a bunch of births because it's rapid growth, and that's where the world was at once. But then it goes over to slow growth where you see that the base is kind of the same as the middle-aged population. So I'm meaning that there's not much growth happening; it's all stabilizing. And then with the no growth and even decline, you have it to where it's actually not a lot of births happening, but then a huge older population. You see this a lot in the Norwegian countries where they have a huge older population, but they have no younger population to go back in the workforce or to push back into the economy. So they're really gonna hit.
That's why they make immigrants.
Yeah, be some type of immigration or some
To
type
support
of
their-
incentive to give birth for their population, for them to basically excel the population growth.
Yeah, basically. So this chapter also goes into like all the things that are going to limit our population eventually, and all that how we're
Source of
destroying the
water.
earth and whatnot,
Source of fossil fuel, source
Fossil
of water,
fuels,
source
all the-
of land,
all the
source of-
terrible things people are doing. Oh no. All right, well.
Oh no. We ain't gonna be alive to see that, hopefully. But yeah, that's pretty much sums up ecology. It's pretty ecology is a pretty straightforward unit, but it's a lot of information that you need to know. You need to recognize what these graphs mean. You need to recognize K-selected, R-selected species. You need to know what's exponential growth. What does carrying capacity look like? What does stabilization look like? How will certain environmental factors affect a density-dependent species or population, rather than a certain environmental factor will affect the density-independent species or population. But definitely, it's an interesting chapter because it has to do with us, has to do with life, has to do with our future, the Earth's future, our future generations to come. And if we don't learn how to manage population growth, how to not manage carrying capacity, environmental factors, if we don't manage the natural environment around us, then we're basically doomed.
All right, that sum it up.